Welcome back to The Explainer. Today, we're diving straight into a massive breakthrough out of Imperial College London, and it tackles one of the absolute most frustrating roadblocks in quantum computing right now. We are talking about Clavina. It's a brand new, literally shape-shifting architecture for photonic quantum computing. Now, if you follow the race for the ultimate quantum supercomputer, you already know that computing with light is, well, it's one of our most promising pathways. But honestly, it has not been easy. So we're going to unpack this major study just published in Nature Photonics because they might have actually found a real working solution. Real quick, here's our roadmap for today so you know exactly where we're headed. First, the photonic computing problem. Then we'll meet the Clavina architecture itself. Third, testing the shapeshifter. And finally, a fault-tolerant future.
All right, Section 1, the photonic computing problem, computing with light. To really appreciate just how big this breakthrough is, we've got to talk about the wall scientists have been banging their heads against for years. It all boils down to this really fascinating physical riddle. How do you actually compute with light if the particles absolutely refuse to interact with each other? It sounds like a little, right? But this has been the literal roadblock sitting right in the center of quantum physics research. Let's think about our main character here, photons. These are light particles. And look, they are phenomenal carriers of quantum information. I mean, they move at the speed of light, naturally, and they don't easily leak their data into the environment. But here's the catch. The paradox, really. They lack natural interactions. It's kind of like when you see two laser beams crossing in a sci-fi movie. In reality, they just pass right through each other like ghosts. So while they carry data perfectly, their total inability to naturally interact makes the complex, multi-step math you need for quantum computing incredibly difficult to pull off. Historically, to get around this, researchers had to build these massive, highly specific optical circuits. Basically, traditional photonic systems were one-trick ponies. They were built for one highly specific task, and if you wanted to solve a different problem, you were looking at a complete physical hardware overhaul. Super rigid, super inefficient. But that's where this new Nature Photonics study completely changes the game with the Clavina architecture. Clavina is reconfigurable. It's modular. It's basically a shape-shifting platform that combines both linear and nonlinear quantum operations all in a single system, which finally overcomes those frustrating old limitations.
Moving on to Section 2, meet the Clavina architecture, modular design. Let's look at how the team from Imperial's Department of Physics actually solved this massive hardware hurdle.
To crack this, they actually drew inspiration from something you probably have sitting on your desk right now. Clavina was directly inspired by modern classical computer processors. Think about your standard PC. It combines specialized components, right? You've got a CPU for general data, a GPU for graphics, maybe some dedicated AI chips. Well, Clavina takes that exact same modular logic and applies it to quantum photonics. Instead of building one giant, inflexible machine, they built a system out of specialized, interchangeable parts. It's brilliant. So in practice, it works in three main steps. Step 1, a central control unit actively directs the quantum info, telling it where to go. Step 2, that information hits this highly programmable optical network. And step 3, the data gets routed into specialized nonlinear modules for the actual processing. The genius here is that Clavina dynamically moves data around to perform completely different computations, and nobody has to swap out the underlying hardware to do it. You just utilize different functional modules based on whatever math you're trying to achieve. Dr. Shang Yu, the lead author on this study from Imperial, he sums it up perfectly. He says, "Our new architecture, Clavina, is scalable, modular, and extensible, allowing different functional modules to be used depending on the computational task we wish to perform." He mentioned they wanted to provide a complete step change in functionality over older designs, and man, looking at this structure, they absolutely hit the nail on the head. All right, Section 3, testing the shapeshifter, proving the concept. Because look, theoretical architecture is awesome on paper, but physical proof is what actually moves the needle. So to prove Clavina actually worked, the team ran a single, unchanged piece of hardware through a total gauntlet of complex tasks. We're talking simulating the Bose-Hubbard model, generating Gottesman-Kitaev-Preskill or GKP states. And as co-author Ying Dong pointed out, this exact same setup can also solve graph problems and create large entangled states. I mean, that sheer versatility from one single system, that is exactly what the quantum field has been desperately waiting for. Let's actually zoom in on that first test for a second. Simulating the Bose-Hubbard model. This is a really famous problem in condensed matter physics about how quantum particles interact. Dr. Jinjiao Sun from Queen Mary University highlighted that by mixing linear and nonlinear operations, Clavina successfully managed these super complex many-body interactions. The big takeaway here? Simulating many-body interactions is so ridiculously hard that even today's most advanced superconducting quantum computers struggle with it. But Clavina's light-based system handled it beautifully.
And then they tackled something even more crucial. They generated those GKP states. Okay, let's translate that dense physics jargon for a second. Just think of GKP states as specialized shields. They encode quantum information in a way that protects it from background noise and errors. And here's why this is a massive deal. Before this, photonic systems could only generate these shields probabilistically. It was literally a roll of the dice. You couldn't guarantee they'd be there when you needed them. But Clavina, it produces them reliably, on demand. Boom! That removes one of the single biggest barriers to practical quantum computing. Which brings us to our final section, Section 4, a fault-tolerant future, error correction. This right here is the ultimate endgame we're all looking for, self-correcting quantum computers. Look, today's quantum computers are noisy. They're prone to these tiny microscopic errors that can just absolutely wreck massive calculations. But since Clavina can reliably generate those protective GKP states we just talked about, it provides the exact foundational building blocks we need for quantum computers to natively detect and correct their own errors.
To really solidify how huge this is, listen to Dr. Raj Patel. He leads Imperial's photonic quantum computing program. He said, "The nonlinear operations in our architecture provide a universal gate set at the physical level, which is required for the future implementation of bosonic error correcting codes." Okay, in plain English, Clavina isn't just some cool new way to process light. It's providing the universal, physical foundation we actually need to build quantum computers that won't just fail every time there's a little background noise. As this tech scales up, the platforms that can adapt without needing entirely new physical designs are going to win the race. So it leaves us with a pretty massive question to ponder. Will modular, shape-shifting architecture like Clavina become the definitive blueprint for the error-free quantum computers of tomorrow? Given the crazy versatility and error correction potential we've looked at today, it sure seems like the future of light-speed computing has finally found its form. Thanks for joining me for this explainer, everyone. Keep your eyes on the horizon because this quantum leap, it's already here.